So the X in X1 stands for X-rays. So I suppose we'd better have a little bit of a look at some of the relevant history of X-rays and what they are before we get started, so we know what we're talking about. And it really starts with devices like this, a Crookes tube. You might remember them from school or university. A sealed glass tube with most of the gas removed, and a couple of electrodes, electrode at one end and then another one in the foot at the near end there, with the cruciform cross mounted as the metal electrode. And so the negative end is the far end, the one on the right, where you can see the red glow, and you've got a high voltage between the cathode, the negative end at that end, and the end with the cross, the anode, the positive end. And not only does the remaining gas inside the glass tube end up glowing, but something glows green at this end on the rounded end of the tube, and has a very nice and sharply defined shadow of the anode showing there. And this was quite a subject of study, very mysterious as to what was causing this effect. What you notice is that the whatever it is that's coming out of the cathode and traveling through the near vacuum must be traveling in very good straight lines, because it's producing a very sharp shadow. And that was the fundamental demonstration that there was some sort of radiation or particles traveling in a straight line. And this chap, William Röntgen, looks like a classic mad scientist here, and he's got a Crookes tube in the picture on the right there. He was working with it, and he noticed that when he was doing so, that a board covered in phosphorus compounds across the other side of the laboratory would start glowing when the Crookes tube was turned on. And it would even do so in the case where it was covered by a layer of paper or thin card. And what he realized from this was that he had discovered a new form of radiation that must be coming from the Crookes tube and was penetrating through that thin cardboard and causing the phosphorescence on his specially coated board. Of course, he went on from there and started producing amazing pictures here, the first X-rays of a human hand. He's got his assistant, excuse me, I'm just letting some more people into the meeting who have joined us. All right. So you can see here the bones in the hand and the soft tissue in a sort of lighter grey colour, but particularly the metal there of the wedding ring or the trinkets around the wrist, blocking the penetration of the X-rays very effectively. So he started to realise that this might have all sorts of interesting applications. So what are these X-rays? Well, they're part of the electromagnetic spectrum, and this diagram really shows the whole of the electromagnetic spectrum as we understand it, with the long wavelengths on the left in the terms of radio, where the wavelength's about the size of a building, through to shorter radio waves and microwaves, where the wavelength's in the order of centimeters, so the size of people or the size of your hand. The microwaves that you use for cooking are 12 centimeters long. And then you come down to things the size of insects. Smaller than that, we get into the infrared radiation, and we're down to the sort of the size of the tip of a needle or something like that. Into the visible part, you find that you can study single-celled protozoa like amoeba, but you start to lose the ability to go any further in the visible part because the wavelength becomes comparable with the size of the object. Ultraviolet is good for molecules, X-rays, you're now into the realms of atoms, and gamma rays right down into the realms of the atomic nucleus. So a huge range in wavelengths, 15 powers of 10 shown on this diagram. And the visible part, of course, is just that tiny little section in the middle there. But the X-rays are really quite short wavelength and very high energy. And what Röntgen realized was that what was going on in those Crookes tubes was that the heated filament at the cathode was releasing electrons boiling away from the metal. They were being accelerated across the gap by the high voltage, picking up a lot of energy and then striking the metal in the cruciform, in the anode. And it was the electrons striking the metal that was causing that metal to then release the X-rays in various directions. And so now this is a more up-to-date diagram of an X-ray gun that you would use when you're going for a medical X-ray to attempt to produce a fairly narrow beam by having a slug of metal mounted solidly and at an angle, so that the X-rays tend to come out one side and you get them more directed. And then of course they put shielding around the rest of it to stop it going in every direction. And so the effect is you have quite an intense beam of electrons coming from your X-ray gun here. You shine it through whatever part of the patient is of interest and put the photographic plate behind it, and the X-rays cause the image to be cast onto the plate. Fairly straightforward idea. But we've gone beyond that these days. Rather than just these simple two-dimensional shadow casts that you're probably familiar with, we have these amazing machines called CT scanners or CAT scanners, and the patient goes inside the machine, and what you have is a circular track which carries a detector and an X-ray gun mounted 180 degrees apart, and it shines a beam of X-rays through and then steps around until the whole lot has rotated through 360 degrees. So it's put a beam of X-rays through at every possible angle and picked up the resulting intensity. And then with some very clever mathematics, you can do an inversion of the data that you get and create a 3D map of what's going on inside the patient. So you get a 3D X-ray. And next week's talk is about how to CAT scan the whole universe. And so we'll come back to that then. So what about X-rays specifically in astronomy? And this is an iconic picture here of the Chandra spacecraft and an image of the Bullet cluster, where the red pinky material is actually X-ray emissions. That's a key piece of evidence to do with the subject of dark matter in this photograph, but that's the subject of a whole different talk. But you notice we were talking about using a spacecraft. The problem with X-ray astronomy is that our atmosphere acts as a very effective shield for all of the high energy parts of the electromagnetic spectrum. Everything from ultraviolet right through X-rays and gamma rays is very efficiently blocked by our atmosphere. And so this chart at the bottom here tries to show that almost none of the gamma rays or X-rays make it to the ground until you get down into the ultraviolet, when it starts to let things through. Our optical telescopes work, as do our eyes, on the visible part of the spectrum down here, and some of the infrared light gets through, some doesn't. Some is absorbed by things like water and carbon dioxide and so on. Then a huge slug of the infrared and into the microwave region is absorbed, and then there's the window where radio telescopes operate down here. But again, once you get beyond a certain length of wavelength, it goes back to blocking. And so if we want to observe anything really but infrared or optical or radio, then we need to get above the atmosphere, and the ideal way to do that, of course, is to go to space. And so perhaps the most famous X-ray telescope is this one, Chandra, a very unusual looking shape. You can see the classic solar panels and the lens cap open on this end, but the great long length of the tube there is a giveaway that there's something unusual about this telescope. It's very long for its diameter. And that all comes down to the fact that it's very difficult indeed to focus X-rays. With normal light, it's easy. We bounce the light off a mirror or we bend it through a lens. But no one has ever managed to make an X-ray lens. Most material is sufficiently light in density that the X-rays just pass straight through it. Otherwise, the initial application of using it to create shadow mask X-rays in medical applications just wouldn't work. And likewise, it's quite difficult to reflect X-rays. But they have developed a very cunning technique for producing a focused image, which is used in these sorts of telescopes. And it uses 2 or more sets of concentric metal mirrors that are figured either in parabolic or hyperbolic shapes to arrange for the incoming X-rays that come in more or less parallel to be deflected into a focal point. And then of course you can put your camera down at the focus there and make an image. And as it shows in this diagram, you have to have them be very long indeed. It's typically 10 meters. I think Chandra might even be 15 meters long. And this works because of a phenomenon called grazing incidence. If we have a mirror, a typical optical mirror, light would come in and strike the mirror surface and bounce off with the usual law of reflection of the equal angle. And even if it comes in at a very narrow angle, it will still bounce off like this. X-rays, though, when they come in from a steep angle against the mirror, they will just go straight through as if there's nothing there. But if you arrange them to be coming in with grazing incidence at a very, very narrow angle like this, then you can get them to reflect. And that's shown in the diagram on the right, that the angle that you get depends on the characteristics of the refractive index of the material. What's really happening is that the X-rays are so short in wavelength that the gaps between the atoms appear very wide to them, and so they sail straight through without really hitting an atom at all most of the time. But if you come in at a very, very narrow angle, then those gaps appear to close up. It's a bit like looking at a post and rail fence. If you look at it from 90 degrees face on, you can see almost straight through the fence. The posts really don't provide any obscuring nature. But if you go and stand right next to the fence and look along the fence line, then you'll find that all of the fence posts add up to a complete obscuring of your view through it. And that's what these things try to do. They try to bounce the X-rays off at grazing incidence once, twice, sometimes even 3 times to increase the degree of coning into a focus. And it's amazing what we can do with them. Here's the Triangulum Galaxy M33 shown in a combination of optical and infrared light on the left, and the X-ray view of it on the right. And you can see it's really quite a sharp image, none of your blurry nature to this. You can make out individual really hot star clusters in the middle there, and very hot gas as well. I say very hot because it's hot things that produce high energy light in the form of X-rays. Cool things, of course, produce low energy light in the form of infrared. So back to the story of the specific object we're going to talk about this afternoon, and that's Cygnus X-1. It was first discovered actually by a mission inside the atmosphere, but launched high up into it on a rocket, a so-called sounding rocket, sent up into the stratosphere from the White Sands missile base in America, carrying with it Geiger counters that could detect incoming X-rays, and they scanned the sky by spinning the rocket so that the Geiger counter's view rotated around, and then as the rocket tipped over, it would sweep across the sky as well. So it created quite a wide field of view for the experiment. And they actually used this and detected a number of X-ray sources coming from this deep space. And we're talking about radiation here with wavelengths around 1/10 of a nanometer. So that's 1/100th the size of an atom or something like that. Now, they tracked down 8 of these X-ray sources from that particular experiment to an approximate region in the sky. And this particular one, the first one they discovered, they named Cygnus X-1 because of its position in Cygnus, roughly along the neck of Cygnus the Swan there. But obviously with just a Geiger counter and a spinning rocket, you don't get very good spatial accuracy. And so they had a sort of vague idea that it was in Cygnus, but not a particularly refined location for it. So the next step was the first X-ray satellite, which was Uhuru, and that found 300 more X-ray sources in the sky in the 1970s. But again, the detection accuracy wasn't very good in terms of being able to pin these things down to an exact spot on the sky. But the next year, the radio astronomers got in on the act, and 2 different teams of radio astronomers were scanning the sky and found a radio source that they were able to pin down to quite a narrow angle just next door to the star Eta Cygni. So that's the 4th magnitude star that's in the neck of the Swan there on that map that we had just now. But the real discovery, the real first image of it, actually goes to the balloon launched missions. Quite incredible. These would send a, looks like a dustbin, doesn't it, going up on the tail there of a high altitude balloon way up into the stratosphere. Now these of course have the advantage that they can hang around for quite a long time and make lots of observations over and over again, rather than a rocket which only had a very brief flight time. And this actually produced the first bright X-ray image shown in the middle there of Cygnus X-1. Still nobody knows what it is at this point though. It's a great mystery. But it wasn't long before they noticed that when you studied it and looked at it with various instruments, you noticed that the brightness, the power output of it, was flickering on a time scale of several times per second, so 0.3 of a second or thereabouts. And that's a very fundamental thing to notice about an object, because whatever the energy source is, if it's flickering in under a second, then it must be less than 1 light second in size. And 0.3 of a light second is around 100,000 kilometers. And that's 15 times smaller than the sun. The sun is about 1.5 million kilometers in radius, I think. So really quite a tiny object. And the reason for that is that whatever the physical process is that's causing the thing to brighten and fade in the process of flickering, some of the light is going to be coming to us from the near side and some from the far side. And so the flicker will begin when the near side light arrives and will continue to be observed until the light from the far side has arrived. And the difference in the time of flight is the speed of light divided by the size of the object. So if there is a very quick flicker, then it must be a very small difference in the flight times between the near and far side of the object. And so you can constrain the physical size of this thing. Now that's very interesting because this is a very bright source. And if it's very bright and very small, then it means it must be very, very hot indeed. But the optical astronomers are now getting involved because they've got a location to go after. And what they notice at this particular point in the sky is a blue supergiant star. Mass estimates 20 to 40 times the mass of the sun, and blue hot, a temperature of 31,000 degrees Kelvin, and about 5 million years old. And this is in a cloud of such supergiant stars, about 6,000 light years from the Earth, 6,070 they now measure the distance as. And whilst there's a certain amount of gas and dust in the middle that's between us and the object there that's dimming it, making it appear less bright, if it wasn't for that intervening dust, this would be a star that would be really quite bright and we would see it with the naked eye. But actually it's dimmed sufficiently by all of the dust that we need a telescope to spot it. Turns out that this is one member of a group of such hot blue supergiant stars in what's called the Cygnus OB3 association. Here's a partial diagram of the galaxy. Here's the sun and the nucleus of the galaxy in the middle here. And we live just in the unfashionable suburbs of the Orion Spur here, which is a thin and weedy bit of spiral arm. And if you trace the Orion Spur back, it merges back here with the Sagittarius arm. And it's at about that merge point, about 6,000 light years away, that this large cluster of these very hot blue stars exists. And the diagram on the right shows, with little yellow rings around them, all of the main members of Cygnus OB3, all of these stars that were probably all formed around 5 million to 7 million years ago in a collapsing nebula, and then have begun to scatter themselves around the galaxy all on their own independent orbits. And the Cygnus X-1 blue supergiant is one of the outliers of the group over on this side here. It's actually probably the one that's furthest from the center of the whole group. Biggest member of the group weighs in at 40 times the mass of the sun, and the fact that we still see that means that anything with a mass of 40 solar masses or less is probably still carrying on its life as a main sequence star, but anything over that has probably suffered the usual massive star death process of exploding as a supernova, perhaps turning into what's called a Wolf-Rayet star first. And we still see the Cygnus X-1 star as around about a 20 to 40 solar mass star, so it's under that limit. That all makes perfect sense. But we don't really think that the blue supergiant can be the source of the X-rays. For one thing, it's too large. That fast flickering really would preclude it being able to be such a large star.
What's that? Go have a look.
But studies of the blue supergiant revealed that when we look at its spectral lines in great detail, the lines in the spectrum are moving to the right and left in the spectrum to higher and lower energies, being blue and red shifted as it is orbiting a massive companion. And we don't see that companion. Here's the graph of the Doppler effect. And so what's happening is that the two stars or two objects are orbiting around each other every 5.6 days, which is quite a tight orbit. It's only 0.2 astronomical units. That's roughly the same size as Mercury's orbit, perhaps actually even smaller. And the whole thing's tilted by 48 degrees compared to our line of sight. So we don't see it as an eclipsing binary. We don't see the one star getting in front of the other at any point because of that. But given that we have a mass estimate for the blue component, and we understand Kepler's laws and Newton's laws of gravity, we can work out that the other companion that we haven't detected has a mass of 14.8 solar masses. Now that's way too big for it to be a neutron star. A neutron star would top out at about 2.5 to 3 solar masses, what's called the Tolman-Oppenheimer-Volkov limit. Any more mass than that, and gravity wins and turns you into a black hole. So we're way above that mass. And this tends to suggest that the only candidate for a small compact object, and remember that fast flickering means it must be small, for it to be that massive, suggests that it's probably a black hole. The size for a black hole event horizon for a 14.8 solar mass object would be 44 kilometers, which is much, much less than the 100,000 kilometers that we had as the upper limit from that flickering. But nevertheless, this could well be the answer. However, instrumentation improved rapidly. 1973, they managed to measure the brightness flickering on timescales not of a fraction of a second, but down into the milliseconds. And that means that we're talking about an object that is 1 light millisecond in diameter, and that's 1,000th of a light second, which works out to be 300 kilometers. And so it's no greater than 300 kilometers in size, and a black hole would be 44 kilometers for that mass. So we're starting to really bring these two estimates quite close together. Again, it's all down to that difference in the arrival time. There's a diagram showing that flickering. You can see the brightness here over time, really a lot of very spiky, sharp peaks in the brightness there, indicating very, very rapid changes in the power output. Jumping forward about 20 years, we think we've detected the event horizon of this black hole now. We've looked at the spectrum of light from matter falling in towards the black hole and being eaten by it. And you can see how the light coming from the matter that's falling in gradually takes on a greater and greater redshift as it falls down the gravity well, until it suddenly disappears. And if it was falling in and hitting some solid object, there would be a flash of energy due to the impact as the mass of the incoming object was absorbed. But that's not what happens when it passes through an event horizon into a black hole. You just see a dying pulse train which fades away. And that is what this is observing here from the matter falling in. Very much consistent with the idea that the black hole is eating material. And so we put all of that together and we get an artist's impression of what's going on here. The two objects are quite close together, the blue supergiant and its companion, a black hole. And because the blue supergiant has gone into the giant star phase and expanded its outer layers, they are no longer as tightly held to the main star. And the strong gravity of its companion here is able to pull the material across in a bridge of infalling matter, which goes into a death spiral, into what's called an accretion disk. And as it spirals inwards, it loses gravitational energy, and that turns into kinetic energy of motion. And then the material crashing together causes it to get very, very hot. And so the inner part of the accretion disk can end up at a very, very high temperature. It's just a diagram of effectively what's going on with gravity. If you have two objects, both with sort of roughly equal masses, there's a point of balance between them, which you can easily work out. It's just in the ratio of their masses. And anything within this lobe is attached to this star, anything that's within this lobe is attached to this one, but any matter from this star that escapes in the form of its solar wind or other ejector coming out as coronal mass ejections is going to sink down and be captured by the gravity of the companion. Now we can also look at this X-ray emission in more detail by looking at the spectrum of it to try to work out what the material is made of. There's a diagram here of a little X-ray spectrometer. We have our X-ray tube or X-ray gun, again with a cathode and a slug of metal, and we bounce the X-rays off our sample onto a crystal that acts like a diffraction grating. All of the nicely arranged atoms in the crystal act like lots of very tightly ruled lines and bounce the X-rays off the crystal at an angle that depends on their wavelength. So we can split them up in the same way that we use diffraction gratings or prisms to split up visible light. And when you do that for a particular sample of material here, you get a spectrum that looks something like this, very neatly stylized. And it composes two parts. One is the typical curve here with a rise to a maximum and then a long slow tail off down to longer wavelengths. So this is the high energy end, short wavelengths as a maximum cutoff, and then the longer lower energy wavelengths down this side. But then superimposed on this so-called black body curve that you get here, which is just thermal emission of X-rays due to it being very hot, you get particular emission lines caused by particular elements. And those, it turns out, are extremely useful in telling us exactly what something is made of. Because in one of the best results in science, I think, this is Moseley's law for the wavelength of the emitted X-rays for different elements. Each element has a characteristic atomic number, which is just the number of protons, the number of positive charges in the nucleus. And so element number 3 here at this end would be lithium, and we would go all the way along here, and number 26 would be iron, and so on. And if you look at the position of the emission lines for the highest energy emission line, you get a lovely fit of a straight line here on this graph. It's actually plotting the square root of the wavelength up here. That's because of that z squared in the formula, but we won't go into the maths. So a beautiful fit. So if you measure the wavelength, you can immediately read off which element it was in a very straightforward whodunit. And that's because the process that's involved is that the incoming electron is hitting an electron in the material of the sample. It might be an X-ray coming in, it doesn't have to be an electron, but it hits it and knocks it clean out of the nucleus, clean out of the atom. And then what happens is that the next nearest highest electron in the second orbit around the nucleus drops down from orbit 2 to orbit 1. And when it does so, it gives out a characteristic quantum of energy, which corresponds exactly to a particular wavelength in the X-ray spectrum. And the energy of these levels depends entirely, in a nice manner, on the number of positive charges that are doing the attracting of the electrons. And because it's the innermost electrons that are involved, there's no problem about the interaction with all of the other electrons in the atom. They are outside of this. And so this particular transition gives us that very, very characteristic and easy to understand spectrum. However, when you put it into practice, it's a little bit more complicated. This is the X-ray spectrum of Cygnus X-1. This line along the top here is the observed spectrum, Gets a little bit fuzzy down at this end because these are the very high energy photons, and it's getting harder to measure them. But what it's composed of is three pieces. It's composed of the black body radiation curve and the iron emission line. There's a lot of iron. This is because there's generally a lot of iron formed in the nuclear processes that go on in giant stars, and so we get quite a lot of iron in the material that's doing the X-ray emitting, and it shows up as a little bump there, but we can measure the peak of that and attribute it to iron very closely. And so the overall spectrum is the sum of the disk, the accretion disk's black body thermal spectrum, and the iron in the corona that's above that, and the corona itself, which is the hot gas that surrounds the accretion disk. And you have to try and take apart all three of those and produce a model to work out what's going on. I just wanted to show you that it all sounds very simple in theory, but really these things get rather complicated in practice. Now here's a picture of Cygnus X-1 taken from the Chandra Space Telescope. So you can see it just shows a very bright center getting fainter towards the edge, but it's really quite a high resolution image. And here's the spectrum that comes from that image. Again, it's fairly grotty. You can see the error bars on every item here, but this peak, which mostly consists of one point, you notice, but is relatively easy to identify. The eye is quite good at picking them out. That is the ionized iron near the accretion disk. So it's again showing that it's a process involving a black hole, particularly because that peak has been gravitationally redshifted. We talked earlier about light climbing out of a gravity well being shifted towards the red. Well, this peak has been shifted towards the red by the mass of the black hole, so we can work out how far from the black hole the emission is coming, so we can work out the position in the gravity field. And we can also see that the peak is rather broadened, and that's because the accretion disk is spinning, and so we can measure how fast that's spinning. So you can see that using the details in these spectra, we can start to build up a very good picture of what's going on. So we think that the disk of matter is really quite thin, but about 30,000 kilometers overall diameter. Now, if you've been listening, you'll say, wait a minute, that's a larger number than the 300 kilometers that we'd narrowed down the size of the thing to from flickering. Well, it's really the X-rays are being produced right in the central 10% here, or 1% of the region, in the 300 kilometers. That's where the material is hot enough to produce these X-rays that we were looking at as regards the flickering, and the accretion disk temperature is much lower further out. But you also notice in this diagram we've got these jets drawn. Again, this is an artist's impression. I wish it was a photograph, but it's not. And these jets are spun up by the magnetic field. The black hole itself is spinning very fast indeed, and that twists the magnetic field in the vicinity up into a very tortuous, twisted jet coming off the spin axis, north and south. And the gas can get trapped in that and accelerated as the processes of the magnetic field lines snap and reconnect, can get accelerated to near speed of light type velocities and shot out along the jets. So not all of the matter that spirals in ends up falling into the black hole. Quite a lot of it, in fact, is shot out along those jets. And we can see the effect of the jet here is a marvelous photograph of the region around Cygnus X-1. This over here this is called the Tulip Nebula. But Cygnus X-1 is here. This is the blue supergiant that it's next to. And this arc across the top here, this blue arc, is where one of the jets of Cygnus X-1 is pointing up this way and then colliding with the outer gas of the Tulip Nebula and dumping its energy into a sort of hemisphere. And we're looking at it side on, so we see a sort of brightened arc as the rim of that hemisphere. I've got a black and white photograph of it. Again, there's the lovely Tulip Nebula. Here's Cygnus X-1 here, and it's sending two jets out, one in this direction and one up here, and producing that arc. So if we just pop back, you can see that blue arc there. Slightly different scale on those pictures. And most recently, the observations have started to be made of Cygnus X-1 at even higher energies, looking right into the very, very central region of that accretion disk and looking at gamma rays coming from it. So this is a result from 2006 showing 100 giga electron volt gamma rays. These are very, very high energies indeed. It's the sort of energies that we produce in some of our particle accelerators like the Large Hadron Collider. And evidently nature is doing those sorts of experiments in and around Cygnus X-1. And this is the first time we've detected this sort of really high energy emissions coming from a stellar mass black hole. So I think we're very sure now that this is a black hole. It really can't be anything else. All of the modeling of accretion disks and the spectra and all of the other evidence, the flickering and the size, all points to that. But it was the subject of a friendly wager between two great scientists, Stephen Hawking, shown on the left there, of course, and Kip Thorne on the right. Kip Thorne's published quite a number of books on black holes. And they had a bet, and Stephen bet that Cygnus X-1 was not a black hole, effectively betting against his life's work on black holes existing. And he said it was an insurance policy. But finally, in 1990, so actually 30 years ago now, he actually conceded that all of this data that we've been talking about today added up to so much of an overwhelming case for Cygnus X-1 being a black hole that was eating its neighbor that he had to concede. And just finally, we've got a final image here of the Tulip Nebula superimposed with an enlarged picture of Cygnus X-1 there, and the star clouds of Cygnus all around, with a lot of those other hot blue Cygnus OB3 stars that you can see. And I just want to say a little bit about the life cycle of Cygnus X-1. So the companion star is perhaps, say, 25 solar masses and about 5 to 7 million years old. Its companion, whatever it was in the first place, has produced a 15 solar mass black hole. That's really quite big as these things go. I think the smallest one we've discovered is 5 solar masses, so it's 3 times that minimum limit. So it must have been a very large star, and we know it must have been very large because the 2 stars that are in the binary pair, the supermassive black hole and X-1 itself, would have been born together as part of this overall star forming process in the OB3 association, and they would have evolved, as stars do, at a pace depending on their mass. And so the higher mass object always runs through its fuel more quickly and reaches the end of its main sequence hydrogen burning phase first and explodes as a supernova first. And so Cygnus X-1 must have been larger than its current companion at that 25 to 40 solar masses. Indeed, the rest of the cluster has a 40 solar mass star there that still hasn't yet evolved into a black hole or blown up as a supernova in any other way. And so the progenitor for Cygnus X-1 must have been more massive still than that. So this must have been 50, 60 solar masses. And so you would have had that running through its life cycle with its companion as a main sequence star. X1 exploded. Later on, the slightly lighter companion has now fully expanded into a blue supergiant and is due to explode anytime soon. And it too will form a black hole. And we will then have a pair of black holes orbiting around each other, only around 0.2 astronomical units apart. And of course, as we know, they will spiral in towards each other, giving off gravity waves as they do, and eventually merge. And so in the future, it's going to be an absolutely fascinating thing to watch. But sadly, I think we've got about another 500,000 years to wait before the companion lets go as a supernova. So we won't be around to see it. But future generations of scientists, I hope, will be watching it with great interest. And that's it. Thank you very much for listening.